Welcome to Chapter 26. Today we're going to learn about one of the most important tools that an RF or radio frequency engineer ever has to work with, and that's called a Smith chart. Now, Smith charts were invented quite a number of years ago, and I have to admit that for a long time I had a pretty bad opinion about Smith charts because I thought that everything that they do could be replaced by modern computer calculations, but I don't think that's true. I think that Smith charts give us really powerful insights into what's happening in the transmission lines and the loads that we're working with. And in particular, when it comes to doing the impedance matching, as we saw last time, Smith charts can give us really invaluable insights. They can, in fact, be used to solve problems that would be very difficult to solve any other way. So I want you to have a good opinion about Smith charts because my undergraduate electromagnetic field theory course did not give me such a good opinion. So we're going to talk today about it's a graphical technique. It's a technique that is not going to give us the precise answer to an infinite number of significant figures. I would say it'll probably be good to about 2 significant figures, but I mean, if we're cutting a transmission line, I'm not sure that I can cut a transmission line with a precision that's more than 2 significant figures anyway. So we're going to talk about how does a Smith chart work, how are we going to derive the elements of a Smith chart, and we're going to learn how to plot impedances on the Smith chart, how to convert them to admittances. We're going to be able to determine the input impedance of a terminated transmission line, and we're going to learn how to use it to design a single stub tuner, which of course was the culmination of our work in the previous chapter. Now, as you might guess, the subject of our historical perspective today is the inventor of the Smith chart, Philip H. Smith. He was an American electrical engineer, worked for Bell Labs, and he's best known really for inventing the Smith chart. And really, it was the foundation of radio frequency engineering for decades. It was in fact owned by Bell Labs and by his widow, and then it was most recently purchased by IEEE. So the IEEE Microwave Theories and Techniques division owns it, and happily I've been able to get permission to replicate it here in today's lesson. So we're going to talk about the Smith chart is really a tool that was invented in 1936. In really its current form was available in the late 1930s. Since the 1980s, computer tools have become much more powerful. Pencil and paper Smith charts are not used as often as they would have been used a long time ago, but they're still incredibly useful for visualizing. And so I just want to emphasize that the best thing that the Smith chart does is it allows us to visualize the problems associated with transmission lines and loads. And as an engineer, being able to visualize what's going on, have a picture in my head that explains what's going on really makes all the difference in the world for me. So many computer tools and digital measurement devices today still use Smith charts. You might buy a $50,000 piece of electronic equipment and the screen is a Smith chart. It's really remarkable how effective that Smith chart is at helping you to understand what's going on in that circuit. So Smith charts can be used to plot impedances or admittances. They are a plot of reflection coefficients and many other quantities that really exceed the scope of our conversation here. We only have time for one chapter on Smith charts. You could spend a month or 2 months learning about Smith charts and still not have learned everything that there was to know. We know that the impedance of a transmission line, that is to say the ratio of the voltage divided by the current, varies from point to point, and that the impedance repeats itself. I just want to remind you that we've seen that that impedance repeats itself every half wavelength. That's something that we proved to ourselves last time, and we're going to take advantage of it today by plotting the impedance on a circle. So in the same way that the impedance repeats itself every half wavelength, if you have a circle and if you plot impedances on the circle, then if you are here and you go around the circle, well, when you've gone 360 degrees or 2 pi radians, you come back to that same point. So if we can make it in such a way that this is a plot of a circle, then we will be able to take advantage of the fact that the impedance repeats itself. So one revolution around the circle returns you to the same point, and moving a half wavelength around the line, along the line will also return you to that same impedance. Now, we could have an infinite number of Smith charts that would deal with different transmission lines, but it's better to just have one Smith chart. So we're going to normalize all the impedances in the system by dividing them by the characteristic impedance of the transmission line. So we're going to go from a capital Z. Capital Z is going to be used to represent regular impedances. And we're going to use lowercase z to represent the normalized impedance of the line. Now, it's a little bit unfortunate that this is completely standard, and it's also very common to use lowercase z to represent distance along the line. So I will try to use z prime for distance. So I'll have I'll have a lowercase z for normalized impedance, and then a lowercase z prime for distances. So notice that then if we've divided by the characteristic impedance of the line, then we can really use any characteristic impedance, and it'll all be normalized and it'll all appear on the same Smith chart. So if we take a load, which we're now going to allow the load to be complex, because of course the load could have a resistant component to it. It could also have a capacitive component or an inductive component to it, and either of those in phasor form would yield imaginary impedances. So we're going to normalize that, and we're going to drop the L's on the lowercase r and the lowercase x. So we're just going to call it lowercase r and lowercase x, and that's going to be r plus jx is going to be the normalized load impedance after we've divided it by the characteristic impedance of the line, as you can see here. So we're going to divide the load resistance by z sub c. We're going to divide the load imaginary impedance by z sub c, and that's going to give us r, and it's going to give us x. And these quantities, lowercase r and lowercase x, are going to be super important to us. I'll try to highlight the things that are going to be super important, and those are two of them right there. Now from chapter 25, we derived an equation that allowed us to calculate the input impedance of a transmission line. I'm just sort of popping this back up here because we're going to use it later on in today's lesson. We can normalize that equation. So what we're going to do is if we divide both sides of this equation by z sub c, then of course the z sub c's here are going to cancel. The left hand side becomes normalized, lowercase zn, and then furthermore I'm going to divide both the numerator and denominator of that fraction by z sub c. So I'm going to take this, I'm going to divide it by z sub c, I'm going to take this, I'm going to divide it by z sub c, and that means that each of the quantities in the fraction is also going to be normalized. So capital Z sub L becomes lowercase z sub L. Z sub c divided by z sub c just gives you a 1, and we kind of omit that 1. The 1 here can't be omitted, and then this is the lowercase z sub L right here. So we've normalized that entire function. Now we also remember this equation. Gamma is the reflection coefficient, and gamma of course is really important to us because gamma is going to give us information about what fraction of the incoming signal is reflected back down the line, and that's really going to impact the input impedance. So we know this equation, which again is super important. I probably should have put a box around that equation, but we've already seen it. Way back in chapter 24 we saw this one. Now if you look at that equation, and if we now accept the fact, let me erase this box, if we accept the fact that z sub L can be complex, then that means that gamma can also be complex. The characteristic impedance of the line z sub c will be real, but the load impedance could certainly be complex, and that means that the reflection coefficient can be complex. So we're going to have gamma r, and we're going to have gamma I. So that's the real part and the imaginary part of the reflection coefficient. And those quantities are also super important. So gamma r and gamma I will be very, very important to us. And it's really a relationship between r and x with gamma r and gamma I is really what we're going to be working with in the Smith chart. Now we can rearrange equation 26.7 as we did in fact in chapter 24. We can rearrange that to give us z sub L as a function of gamma. Now I'm going to replace z sub L with r plus jx, and I'm going to replace both occurrences of gamma with gamma r plus j gamma I. So notice that there's a negative sign here and a negative sign here because there was a negative sign in front of this one. So these two terms, including the negative signs, not including the negative sign, both negative signs came from here. So we have now an expression that relates that again relates r and x to gamma r and gamma I. And as I mentioned to you just a minute ago, that's really the heart of the relationship that we're looking at with Smith charts. So we need to separate the right hand side. I'm going to erase a couple of these circles, and I'm just going to mention that what we want to separate the right hand side into a part that is purely imaginary and a part that is purely real. And in order to do that, we need to get rid of the imaginary part in the denominator. This is going to be a theme that you're going to see not only in this class, but in other ECE classes, that you need to get the imaginary part out of the denominator. If the denominator is completely real, then you can separate the entire function into a real part and an imaginary part. So we have to get rid of the imaginary part in the denominator. The way that we do that is we always multiply by the complex conjugate of the denominator, which I guess is is on the next page. But in order to do that, that means that when we do that, it means that the denominator is going to end up being perfectly real. And let's see what that means. So if we're going to multiply by the complex, so here we go, multiply it by the complex conjugate of the denominator. And so since we're multiplying by a fraction here that is the same in the numerator and denominator, then this entire fraction is really just equal to 1. So we're not changing anything, but you'll notice that the only thing that's different between this denominator and this term right here is that this negative sign has become positive. That's what we mean when we say complex conjugate. It means that it is the imaginary part has the opposite sign. So when we do this, now we've got a lot of things to multiply out. So I'm going to do a FOIL calculation here. So this will be the first, and this is the, I believe it's the outer, and I believe this is the inner, and I believe that this is the last. In the numerator, in the denominator though, we have a situation with the difference between two perfect squares, and so we can when we multiply those out, we just get the first term squared minus the second term squared. And that means that this j right here is going to get squared, and that j squared is going to become a -1. That means that the denominator is going to become perfectly real. So you can see that by the time we get to equation 26.11, this entire denominator is real, and there's no j that appears anywhere there. That means that we're well on the path to being able to separate this into a real part and an imaginary part. We can do some simplifications. We're gonna do the cross multiplication of the FOIL terms up on top. Some of them are going to cancel out. Let's see. There's a j gamma I gamma r and a negative j gamma I gamma r, and those are going to cancel. These two terms are identical, so there's going to be 2 of those, and so we can simplify the numerator quite a bit. And when we do that, we're going to find that these terms here are real, and this term is imaginary. They both have the same denominator, so we can break them up into a real part and an imaginary part. And so by doing this now, we've been able to separate the real term. This has no j whatsoever, and this is purely imaginary because it has a j that precedes the whole thing. And so we can now set r equal to the real part. So I'm going to say that r is equal to this, and therefore j is equal to this. We're going to do the real part first. And so you can see that I've just said r equals that thing that is in the first box. And then I've skipped 10 or 15 steps of algebra between 26.14 and 26.15. But we've already done a lot of algebra today, and it's really supposed to be a discussion of how to use the Smith chart, not how to derive the Smith chart. But I just want you to know that I have, in fact, double-checked the algebra between 26.14 and 26.15. Decided not to add two more pages to today's lesson, but you can get from 26.14 to 26.15. What that means, 26.15 is actually the equation of a circle. And I don't know if you remember, but we have like x minus x0, the quantity squared, plus y minus y0, the quantity squared, is equal to r squared. And so we can look at this and we say that if we're going to plot this graph on an axis that has, it's the complex gamma axis. So we're going to have gamma r along that axis and gamma I along the vertical axis. Just as we do a complex plane for other things, we're going to do a complex reflection coefficient plane. Notice then that this is of the form gamma r squared plus gamma I squared equals some number squared. Well, the center of it, the center of that circle, this is the equation of a circle, and the center of the circle has an x value. This takes on the form of x0. Y0 is equal to 0 because there's nothing that's being subtracted from the gamma I, and this is the radius. So the center of the circle is, it has an x value of r over r plus 1. It has a y value of 0, and the radius of the circle is 1 over r plus 1. So while it's the equation of a circle, it's the equation of a circle that has a parameter r. So if you give me a value of r, I will draw you a circle. And so we can actually take many different values of r, and we can draw many different circles. And that's kind of what I've done here using MATLAB. So if r equals 0, you can see that I've drawn this outermost circle, and all of them have their center is on the x-axis, because remember that the y component of the center was equal to 0. The center is moving toward the right at the same rate that the radius is decreasing, so all of them pass through this point right here. That's a very interesting thing about these circles. These are known as R circles. And so the R circles really correspond to the real element of the load impedance. Remember that the normalized load impedance, that's a lowercase z sub L, is equal to R plus jx. So when I'm talking about R, I'm talking about the normalized real part of the load impedance. Now we can do the same thing with the imaginary component. And if you go back up to that equation where we had separated the real and the imaginary out, I've just set the two imaginary parts equal to each other. And again, 10 to 15 steps of algebra between these two equations, but I again end up with an equation of a circle, where the center is, we have x sub 0 is equal to 1, so we have the 1 right there, and we have the y sub 0 is equal to, it's kind of unfortunate that we have x being used for two different things here, but it's equal to 1 over x, where x is the imaginary part of the normalized load impedance, and then the radius is also equal to 1 divided by x. So again, now if you give me a value of x, I can draw you a circle. And the x, by the way, can be either positive or negative. Up here with the R circles, we never did any negative resistances because negative resistances aren't physically possible. But negative imaginary impedances certainly are. We can have negative imaginary impedances simply by putting a capacitor into the circuit. So we need to account for x being positive and for x being negative. And that's what this next MATLAB plot does. You can see that I've got a series of circles. They're all going to be along the line x equals 1, and their centers are being adjusted at the same rate that their radii are being adjusted. So again, every single one of those circles passes through the same point. Notice that that we have here. This is the x-axis. The it's the gamma r axis. Everything up here is x is greater than 0, and everything down here x is less than 0. And so we can think about when we're drawing these x circles, they're either going to be in the positive in the top half plane or in the bottom half plane, depending upon the sign of x. So we have R circles and we have X circles, and we know that they both must be true. If that one equation that we saw, let me flip back up so you can remember what that one equation looked like. We know, and we derived this, we know that equation 26.13 must be true, which means that the real parts must be equal and the imaginary parts must be equal, and that means that both the R circles and the X circles must be correct. So I'm going to plot the R circles and the X circles on top of each other. So again, now I've combined them together. Now I'm really just focusing on the region inside R equals 0. This is the R equals 0 circle right here. And so anything that's outside of that circle doesn't matter. And it's difficult for me in MATLAB to get rid of this stuff and this stuff and this stuff and this stuff. But none of that matters, because if you were outside the R equals 0 circle, you would have negative real resistance. And that's not possible. So it's only the part that's inside that circle that matters. Now notice that the X circles, a lot of them are not being really, they're not prominent, but we're really only seeing the arcs of the X circles. So they don't look like circles anymore. They look like just curves. They look like arcs. But I want to remind you that if I flip back up here to this picture, they are circles. It's just that the region within which we're looking right now is not going to see the entire circle. So if you look over here, you can see most of say this circle right here. But when we get to the outer circles, boy, this circle would be way off the top of the screen. So I can't even imagine what that whole circle looks like. But every one of the X circles is a complete circle. It's just that we're only seeing a portion of it. This, by the way, is a Smith chart, a combination of R circles and X circles for different values of lowercase r and different values of lowercase x. That's a Smith chart. And this is what a professional quality Smith chart looks like. And I'm going to have to zoom out a little bit here so that you can see the whole thing. So let's zoom out so you can see the entire Smith chart at one time. And there we go. So that's the full Smith chart. And if you look at your copy of the chapter, you can see that there are numbers written on each of the circles. Those are the R numbers. So I'll erase this in a second. But these are the R numbers right here. And then there's also, around the perimeter, there are these numbers, and those are the X numbers. So those are the indicators of which X circle you're on right there. So what we can do with the Smith chart, there are lots of things we can do, but the first thing we're going to do is we're going to plot impedances. We're going to plot normalized impedances. And so when we're plotting those normalized impedances, we're going to look for the intersection between an R circle and an X circle on the graph. So let's do these examples here. Z sub L equals 0 plus J 0. So that's going to be, if I'm looking for the R equals 0 circle, that's going to be this one right here. So that's somewhere around the outer perimeter of the circle. And because it's plus J0, there's no deflection up or down. I'm actually right at that point. I'm right at this point right here. That's the point A. So that's R plus J0. The next one is Z sub L equals infinity. Well, I don't know if you can see, but as the numbers are, as I'm working my way toward the right here, this is 2, and this is 3, and 4, and 5, and 10, and 20. And as it turns out, we approach infinity at this point right here. Let me erase those circles. And this is the point infinity. So this is point B. And we have 1 plus J0. So 1, let's see, this is the R equals 1 circle right here. Plus J0, well, again, I'm not going to go above or below the horizontal axis, so that's just this point right here in the very center. And it turns out that that's a very important point. So we'll come back and talk about that more later. Then we have 0.5 plus J 0.5. Let me just double check that that's what's on here. 0.5 plus J 0.5. So now I'm going to look for the 0.5 R circle, and that's this R circle right here. And it's plus J 0.5, so I know it's going to be in the top half plane. So I look at these numbers over here. That's 0.3, that's 0.4, that's 0.5. So I'm looking for a point that's along this arc. It's along that arc, and it's along that line, so it's this point right here. And I'm going to get rid of the intermediate things that I drew here, and I'm just going to leave that point behind because that is point E. And then I have 1.5 minus J 1.5. Okay, so looking over here, this is 1.4, this is 1.6. So what I want is this intermediate circle right here. So it's somewhere along this intermediate circle right here. And then it's minus J 1.5, so it's going to be in the bottom half plane. I'm looking down here is 1.2. It's actually negative 1.2, although it's not drawn in there. It's assumed that we understand that these are negative values. There's 1.4 and there's 1.6. So again, I'm going to take this intermediate curve right here, and it's going to be the intersection of those two. That's where this point is going to be located, and that's point E. And then 2 plus J1, 2 plus J1. So this is the 2 circle, plus J1 is going to be above the axis. So when I look at the J1, that's this curve right here. And so I'm at the intersection of those two. And so that's point F. So plotting impedances is really just a matter of figuring out the intersection between the real circle and the imaginary curve. Remembering that that curve is actually part of a circle, but we're only seeing the curve. And we can plot any real and imaginary combination on the Smith chart. Okay, now we can calculate the admittance. Remember that the admittance is just the admittance Y is equal to 1 over the impedance Z. So yes, you could use your calculator to do this calculation, no problem, but it's also interesting that you can use the Smith chart. Remember that we knew that gamma is equal to Z sub L minus Z sub C over Z sub L plus Z sub C. In this equation, I've simply replaced each of the Z's with a 1 over Y. I'm going to multiply through by Y sub C times Y sub L to get this equation. I'm going to then re-divide by Y sub C, the numerator and denominator, to normalize it. And then I'm going to factor out a negative 1. For reasons that will become clear in just a second, that negative 1 makes a difference. Also remembering that e to the j pi is equal to negative 1, I can now say gamma is equal to e to the j pi times y sub L minus 1 over y sub L plus 1. But I know from our previous discussions that it's equal to z sub L minus 1 over z sub L plus 1. So looking at this term and this term, the only thing that is different between them, other than substituting y for z, is this e to the j pi. Now e to the j pi is a phase factor that simply says do a 180-degree rotation. And so it turns out that if you wanted to find an impedance and admittance from an impedance, or vice versa, you move pi radians, or 180 degrees, around the circle at a constant radius. So that means that we can just find the opposite point on the Smith chart, and that's going to be the admittance. So I have example 26.2 is asking me to take 3 of the points that I just drew and find the admittance that corresponds to those points. So let's come back up here, and we're going to have 0.5 plus j 0.5. So let's remember which one that was. That's going to be point E right here. Now, I'm going to put a plastic ruler on top of my computer screen, and I don't know how this is going to go, but I'm going to try to draw a line that passes through point E and also through the center of the Smith chart circle. And the center of the Smith chart circle for right now is also point C. But I'm not drawing it through point C per se. I'm drawing it through the center of the circle, the point that corresponds to r equals 1 and x equals 0. So I put my little plastic ruler on here, and I'm going to try to draw a line that goes between those. And I didn't do a tremendously great job of it, but you get the idea. What you want to do then is you want to measure this distance here, and then you want to measure this distance, the same distance over to here. And what I ended up with was 1 minus j, which is this point right here. So when I used an actual ruler on an actual piece of paper, I ended up with this being, I'll call it E2. E2 is 1 minus j, because it's in the bottom half plane. And so the thing is to remember that you want to measure those two distances and set them equal to each other. You could get a compass, you know, the thing with the pointy part and the pencil, spin the compass around and draw a circle, and that will ensure that every point that it touches is going to be the same length. But to be honest, most engineers don't carry a compass around with them, and I'll have a ruler that you can use in class. So I find that just measuring those two distances and setting them equal is the easiest way. So what I found is that, for this first problem, when I invert 0.5 plus j 0.5, I get y sub L is equal to 1 minus j. And if you plug that into your calculator, so let me just say this column is going to be the Smith chart column, and this column is going to be the calculator column, just for comparison, and I also get y sub L equals 1 minus j. So I nailed that one. The Smith chart nailed that one perfectly. Usually we aren't going to get it quite so precise, but in this case it worked out quite well. And I like you to see, like, what is the level of precision we can get from the Smith chart. Okay, the next one that we're going to look at is 1.5 minus j 1.5, and that is point, oh, dang it, I think I called 2 of them point E. So yeah, that should have been point D that we just did. Sorry about that. So that's point D. It was originally point D, and then the one that we just inverted became D2. Now we're actually going to invert point E. So 1.5 plus j 1.5, get out your handy ruler. And this is really hard on a computer screen. It's hard to do on a computer screen. I don't think it hurts the computer screen. But I'm going to draw a straight line there, and that was really pathetic on the other end. Good, it erased itself. That was perfect. Let's try this again. So I'm going to draw, this is much easier with pencil and paper. But you get the idea. You got and it erased itself again. Let's try one last time, and then I'm just going to do it freehand. I think that it's the static interactions with the ruler that are causing troubles. So there's the line. And then we're going to go the same distance from the center point. We're going to go that same distance along this line. And when I do that, I get 0.3. So I'm on this circle right here. And I think that it's like in this neighborhood right here. So that's point E2. Again, it's much easier if you use an actual ruler on an actual piece of paper. And so what I got for the Smith chart there is y sub L equals 0.3 minus j 0.32. That's the best that I can do from the Smith chart. From the calculator, y sub L is equal to 0.333 minus j 0.333. So pretty close. You know, we're within 10%, and if you can get within 10% on a graphical technique, that's usually pretty good. Okay, the last thing that we're going to get here is 2 plus j1. which is point F. So again, I'm going to put my ruler down. I'm going to try to draw a line through the center. That's going to erase itself, I think. Yep. Okay, let's try it again. Okay, I'm just going to draw that line freehand. You get the idea, I hope, that it's going to be like this. And then I'm going to measure this distance here. I'm going to measure this distance here. And what I'm going to end up with is 0.4. So it's going to be like in this neighborhood right here. So that's going to be F2. And when I come back down to the actual in-class exercise, it's 0.4. So with the Smith chart, I get y sub L equals 0.4 minus j 0.22. And when I do it with my calculator, y sub L equals 0.4 minus j 0.2. So I'm pretty close on that one. I'm feeling pretty good about the fact that I can, in fact, calculate admittances simply by drawing a line across and flipping by 180 degrees. Notice that although I was talking a lot about drawing lines and stuff, what we're really doing is we're taking one of the points, and we are this is pretty messy at this point, but we're really drawing an arc, and that arc is going to rotate 180 degrees around to the other point. And again, if you have a compass, that's a good way to approach solving the problems. But with a ruler, you can also solve the problems as well. Just be as precise as you can, because every tenth of a millimeter can make a big every millimeter can make a big difference in the result. Okay, let's talk about the second thing we can do, which is calculate input impedance using a Smith chart. So we have an equation that can be used to calculate the impedance at any point z. And remember that the z, and I probably should call these z prime here just to be consistent. What we know is that if the load, we've defined the load to be z prime equals 0, so anything over here z prime is going to be less than 0. So I just want to remind you of the fact that z prime is less than 0. So when we plug in z, I'll call this z prime equals negative L, we end up with negative elements well, we end up with the opposite sign of those complex exponentials. When I normalize equation 26.22, I get equation 26.23. And you'll remember that this gamma is going to have a component that really, it's the absolute value or the magnitude of gamma, but then it's also going to have an e to the j theta of the load. So theta of the load is going to impact the initial value of gamma. But then what is interesting is that we then pick up this extra e to the minus 2jk times L. And so we have theta of the load, so down here we have theta of the load minus 2k times L. That's going to be the phase angle. But 2k is 2 pi divided by lambda. I'm sorry, k equals 2 pi divided by lambda. So that's where the k becomes, that's where the 2k becomes 4 pi divided by lambda. So if we then take the L divided by lambda as sort of L measured in terms of how many wavelengths it is, then notice that the 4 pi there is indicating that when we have progressed by 1/2 of a wavelength, so when L over lambda equals 1/2, L over lambda is equal to 1/2, 0.5 times 4 pi is going to give us 2 pi, which is 1 complete revolution. So what this graph has just, or what this equation has just proven to us is what we saw earlier, which is that we want 1 revolution to correspond to 2 pi radians, but we also want it to correspond to 0.5 lambda. And this 4 pi in equation 26.25 is why 2 pi radians corresponds to 1/2 lambda. Because if L over lambda equals 1/2, then 4 pi times 1/2 becomes 2 pi. And then we've done 1 complete revolution around the circle. So all of that is to say that if you want to move along the length of the line, so if you want to move, say, from the load toward the generator, you're going to rotate clockwise around the circle of the Smith chart. Remember that clockwise is actually a negative angle, and this negative angle right here means that clockwise, a negative angle is going to move you toward the generator. To move toward the load, you're going to rotate counterclockwise, which is a positive angle. And I've tried to represent that graphically in the next picture here. just essentially, if you want to move toward the generator, you go clockwise. If you want to move toward the load, you go counterclockwise. And in fact, some Smith charts actually show that right on the Smith chart. You'll notice that there's the arrow right here, which says if you're going toward the generator, use the outer ring. If you're going toward the load, use the inner ring. Because these numbers on the rings around the outside, they're measuring in fractions of lambda. And you'll have to maybe zoom in to be able to see this, but this number is 0.01 and 0.02 and 0.03. The number is increasing on the outer ring as you go clockwise toward the generator, and it ends up at 0.48, 0.490. So when you get to 1/2 wavelength, you return back to where you started again. Now on the inner ring, the numbers are increasing as you go in the other direction. 0.0, 0.01, 0.02, 0.03, and we come back around to 0.47, 0.48, 0.49, back to 0. So if you're going toward the load, you'll use the inner ring to determine how far you've rotated around the ring. So let's look at how we would actually calculate the input impedance of a line. So we have a line with a characteristic impedance of 50 ohms terminated in a load of 75 plus j 50 ohms. The line itself is 5 meters long and the wavelength is 1.2 meters. We're going to use that Smith chart above to estimate the input impedance of this line. And I got to say it's estimating because we can't get it to like 4 significant figures, but we can get a pretty good answer here. So I'm going to normalize. This is how I draw a lowercase z, just to clarify that it's a lowercase z. Z sub L is equal to 75 plus j 50 divided by 50, which is equal to 1.5 plus j1. So that's my normalized load impedance. And in this case, the length divided by lambda is going to be equal to 5 meters divided by 1.2 meters, which is 4.167. Well, I say it's equal to 4.167, which is to say that the length of the line is 4.167 wavelengths. So we're always going to measure length in terms of wavelengths. Now we can then say, oh, for lambda, that seems, I thought it repeated every half wavelength, and yes, it does, because if we want to move 4.167 lambda, I want you to imagine well, I don't need to imagine. Where are we going to start? We're going to start at 1.5 plus j1. So let's come back up here. I'm going to find the r 1.5 circle. So here's r 1.5 plus j1 is this one right here. So we're going to start right there. Now, if we wanted to go 4.167 lambda, I want you to imagine we're going toward the generator. So we're starting, let me draw you the picture. We're starting at the load. And what we want to know is when we've gone 4.167 lambda toward the generator, then the question is what will be the input impedance that we would see right there. So what is the input impedance? So we're going toward the generator. We're moving toward the left. So I'll say in the pictures that we've always drawn here, toward the generator is left and toward the load is right. So I know that I need to go 4.167 lambda. So here is a half a lambda. I'm sorry, this is so sloppy. I'm going to erase it in a second. Here is 1 lambda. I've done two revolutions. Here's 1.5 lambda. There's 2 lambda. There's 2.5. There's 3. There's 3.5. There's 4. So I've now done 4 lambda by doing 8 revolutions. But those first 4 lambda didn't do anything. They just returned me back to the same point again. So I can forget all of that. And it's just the 0.167 lambda that really matters. So down here where I said that the length is 4.167, it's really effectively 0.167 lambda. We don't need to worry about the 4. Okay, so how do we do the 0.167? Well, I'm going to draw a line, and I'm going to do my best to use my ruler again. I'm going to draw a line from there out to the outer rim. And, doggone it. I'm just going to use my hand. Let's see. I know that if I did it correctly, I would come through this point right here. So I'm just going to do my best to draw the line, and I would encourage you with the piece of paper that you have in front of you to actually get a ruler and draw the line and verify that it in fact does go through that point. Remember that the center is always this point right here, and if you look real carefully at the Smith chart, it even has a little red dot there at the center to remind you that that's it. Now, I know that I need to, so this is 0.198 lambda. I know that I need to go a further 0.167 lambda, and that's equal to 0.365 lambda. So I'm going to look around the outer rim, and I'm going to find the place where it crosses 0.365 lambda. So here is 0.35, here's 0.36, and right there is 0.365. So I know that I'm going to, and again I'm going to try to just draw this line freehand. I know that I'm going to go this arc right here to go 0.167 lambda. I'm going to figure out what is this distance here, and then I'm going to calculate, I'm going to measure the same distance along this line, and I know that where I'm going to end up is right about here. And that's going to be the input impedance. And I've run out of space in the bottom here, but I'm gonna say Z sub n, which I pull right off the graph. Z sub n is going to be 0.75 minus J 0.8. But remember that that's normalized, and now I have to unnormalize it. Z sub n is equal to 0.75 minus J 0.8 times the characteristic impedance of the line, which was 50, and that works out to be, let's see, that works out to be, wait for it, I'm just letting the suspense build, 37.5 minus J 40 ohms. So that's the input impedance of the line according to the Smith chart. Now I did do the calculation by hand, and I got that it was 41.1 minus J 40.7 ohms. So this is with the calculator, and this is with the Smith chart. So it's the real part is accurate to about 90%. It's about 10% off. The imaginary part is remarkably dead on. But remember that if you can just be off by one little tick mark, and it can make that difference of 10%. So it's pretty good. It's not too bad. So again, just remember that what we did was we normalized the impedance, the load impedance. We then drew a line from the center. So this is Z sub L right here. We drew a line from the center through Z sub L out to the outer rim. Then we moved the appropriate amount of lambda around the circle. We drew a line through that point, and then we found out that this is Z sub n right here, and then we denormalized that value. Okay, and then the last thing that we're going to do with Smith charts, because I know that there's this is a lot of, it's like drinking from a fire hose today. There's a lot of stuff going on. The last thing we're going to do with the Smith charts is we're going to see how to design that single stub tuner that we did last time. Now, it turns out that there is a very important point and a very important circle that's going to be the center of our work with the single stub tuner. And the point we've already seen. That point is that point in the very center, and I've drawn a big red dot on it to clarify that that is the point of impedance matching. So this point right here is impedance matched. That, of course, is our goal when we're designing the single stub tuner, is to arrive at that point. Because there, Z sub L is equal to 1, which means that Z sub L is equal to Z sub C. And that would mean that it was perfectly impedance matched. I'm going to remove that arrow just so that we don't clutter it up. But that's important to remember. Now the green circle corresponds to R equals 1. And that means that the green circle is actually halfway impedance matched. The real part is impedance matched. The imaginary part has not yet been impedance matched. So if I found myself right here, well, then I would know that I'm halfway home. I would know that I was on the green circle, so the real part is perfectly matched. All I need to do is get down to here by adding another complex impedance in parallel. So I need to first of all find my way to the R equals 1 circle. Then I need to add another impedance to get me down to the perfectly impedance matched point. So I've got here a step-by-step process of how we would do the single stub tuner. We would calculate V, K, and lambda if necessary. Normalize the load impedance, plot the normalized load impedance, then we convert it to an admittance. We already saw how to do the conversion to an admittance. We just simply go 180 degrees around the circle. So we can convert it to an admittance because admittances in parallel are going to add. Then we rotate around the Smith chart from the load admittance until you hit the green R equals 1 circle. Determine how many wavelengths you rotated and convert that to the length D1. Because remember, what we've got here is we have a load, and we're going to go back a certain distance, and then after we've gone that distance, then we're going to attach the single stub to it. And this distance is D1, and the length of the single stub is D2. So we're going to figure out what is D1 by figuring out how far do we need to rotate to hit the green circle. Now, when we did this last time, we didn't have any physical intuition of what D1 meant. But what D1 means is that we've moved to a point where the impedance at this point right here, I'm going to erase that line, but the impedance at that point right there is perfectly matched on the real side, but it's not perfectly matched on the imaginary side. We match it on the imaginary side by adding this single stub tuner with D2. So how do we determine the distance of D2? We're going to figure out what is the imaginary impedance that's at that point, that's at this point right here, that we need to cancel out. We need to have a single stub tuner that's going to perfectly wipe that out. And then we're going to plot the point where y stub equals infinity, because that's the same point where z stub equals 0. Remember that we're starting with a short-circuited stub. So y stub equals infinity corresponds to z stub equals 0. Then we rotate clockwise on that line until the imaginary admittance is equal and opposite to the one that we found in step 7. And we determine how many wavelengths we rotated and convert that to a length D2. All of that probably doesn't make sense right now, but I hope that it'll make sense after we've done the example. So let's do an example. A line with a characteristic impedance of 100 ohms is terminated in a load impedance of 70 plus J170. Design a single stub tuner to match the impedance of this load to the line. The relative dielectric constant is 4, and the Smith chart of the transmitter, the frequency of the transmitter is 100 megahertz. So we're going to follow this step by step. So here's step 1. Step 1, calculate V, K, and lambda if necessary. Well, we actually don't need K, but we do need V and lambda. So V is equal to C divided by square root of epsilon r, which is 3 times 10 to the 8th divided by the square root of 4, which is 1.5 times 10 to the 8th meters per second. So far, so good. We're also going to say that lambda is equal to V divided by F, which is going to be 1.5 times 10 to the 8th meters per second divided by the frequency, which is 100 times 10 to the 6th hertz, or 1 over seconds, and that gives us a wavelength that is 1.5 meters. So that's step 1. Step 2, normalize the load impedance. Z sub L is equal to Z sub L, capital Z sub L, divided by Z sub C, which is going to be 70 plus J170 divided by 100, which is 0.7 plus J 1.7. Oh, it's not ohms, it's just a unitless impedance now. So let's then step 3, plot the normalized load impedance. 0.7 plus J 1.7. Let's come up here. I'm going to find the circle that corresponds to 0.7. So that's this circle right here. And then 1.7 is this arc right here. So it's this point right here. So that's step 3. Now I'm going to, you know what, I'm going to go ahead and not try to use the plastic ruler here. I'm just going to see that it is, I know that on my piece of paper that I'm holding right here, it passes through that point on the other side. So I'm going to draw this line right here, which you would draw using a ruler very carefully. And we're going to find that the y sub L is equal to 0.22 minus J 0.5. So this is step 4. This is Z sub L, and this is Y sub L. Now here comes the trickiest part. This is step 5. Rotate around the Smith chart from the load admittance until you hit the R equals 1 circle. And we're going to be moving toward the generator, so we're going to be going clockwise. So if I had a compass, what I would do, and this is going to be a horrible estimation of what the compass would look like, I would draw around until I encounter the green circle. And at the green circle, I would stop. Now, in practice, what I can really do is I can measure this distance here, and then I can find what is a line so then I sort of slide my ruler over here so that I'm finding what is a line that intersects with the green circle in such a way that it has the same length. And as it turns out, it's this point right here. I did a terrible job with that. So it's this point right here. And so that means that this, let's call this L, that has the same length L right there. And so in practice, what I would have done is rotate around until I intersected that point. But in reality, what I did was I measured it with a ruler, and I came up with the same point. So that is that's the rotation. That's step 5. Now, two things we need to do next. Step 6, determine how many wavelengths you rotated and convert this to D1. Okay, so if you extend this line all the way out until it crosses here, I got 0.423 lambda. Now, when you do this, you might get a different value. It's actually, I'm not perfectly on there right now because I'm doing this freehand, but you might get a slightly different value. It's a graphical technique. That's not going to be a surprise. When we come over here, we find that this is 0.180. Let's try this again. 0.188 lambda. And so now I need to figure out how far did I move from this point as I go around the arc. How far did I move to get over to 0.188? Now there's a little complexity here, and that is that there's a discontinuity right here between 0 and 0.5. So I'm gonna say D1. Come back down here and write this in the graph. So this is step 6. So step 6, D1 is equal to, from the point on the far left, 0.5 minus 0.423 times lambda, plus I then went an additional 0.188 lambda. So D1 is 0.265 lambda, which is 0.265 times 1.5 meters, which is 0.40 meters. So I know, let me scroll back up again. I know that moving around the circle, this distance from here up to here, that distance was 0.5 minus 0.423. And then the additional distance that I went here, all the way around to there, that's 0.188. So this is 0.188 lambda, and this is 0.5 minus 0.423 lambda. And when I move that full length, then that turns out to be 0.265 lambda, which is 0.4 meters. And that means that if I go back up here to my original sketch, which maybe was on a different page, when I move up here, yeah, right here, I now know that D1 is equal to 0.40 meters. If I move 4/10 of a meter away from the load, then I'm on the green circle. And now all I need to do is get from that point on the green circle to the red dot. Well, how do I do that? I need to look again at that point that intersects the green circle. So I know two things about that point. Now I'm looking here at the point that has the number 5 on it. I know that it's on the green circle, but I also know that it's on this arc right here. I know that it's on the arc that corresponds to +2, plus J2. So this point right here is 1 plus J2. Now if it was 1 plus J0, I'd be done. I would be perfectly impedance matched. I got to get rid of that plus J2. So to get rid of the plus J2, I need a minus J2. But I have to start let's see, so that was step 7. So this is step 7. I've observed that the imaginary impedance that I need to cancel is plus J2. Step 8, plot the point where Z sub L equals 0, so that's this point right here, and that point corresponds to Y sub L, or Y sub stub. So this is Y sub stub equals infinity, and this is the point where Z sub L equals 0. So I know that it's a short-circuited stub. So I know that I have to have this line right, this point right here, but when I do the flipping of that by 180 degrees to get admittance, I get this point right here. Now all I need to do is march that around the line, again going clockwise because I'm moving away from the short-circuited load. I need to move that until I get to negative J2. Right here I have a positive J2. I need to get negative J2. That means I know negative means I'm going to go downward. I know that I'm going to go into the bottom half, and I need to find the point, and it's right here where it's J2.0. And I'm going to just go around the outer edge here. This is perfectly imaginary. There is no real impedance there. So I've gotten to negative J2. This point now corresponds to 0 minus J2. That negative J2 is going to cancel that positive J2. So how far did I have to march? I'm going to try to draw a straight line up to there, and then I have a straight line over to here, and it's that angle that I moved. And that, let's see, now I'm going to come back down to the place where I'm going to write. Rotate clockwise until the imaginary impedance is equal and opposite to that of step 7. That was step 9. Let me label step 9 up here because we need to, this was step 8, and this is step 9 is figuring out how far did we rotate. Yes. And then step 10, determine how many wavelengths you rotated. So step 10, gotta wait for it to reappear. There we go. So step 10, we know that D2 is equal to, we started at, or we went to 0.324, but we started at 0.250, and all of that's multiplied by lambda. This then is 0.074 lambda, which is 0.074 times 1.5 meters, which is 0.11 meters. And that allows us to see that D2 is going to be 0.11 meters. So in order to balance this line with the load, we need to move back 4/10 of a meter. That puts us on the green circle, and then we need a single stub tuner that is 0.11 meters long. That's going to have an input impedance that is an input admittance that's going to be negative J2, and that's going to perfectly balance the J2 that was left when we moved back by 4/10 of a meter. So, as I mentioned, Smith charts can do so many things. We've really only scratched the surface, but we know that we need to normalize impedances. We know that we have R circles and X circles, and they originally come from these two equations. But when we draw the R circles and X circles together on the graph, we end up with some very interesting results. You can plot impedances by looking for the intersection of the R circle and the X circle. Corresponding admittance is found by rotating 180 degrees. The input impedance can be found by moving a distance clockwise, which is to say away from the load toward the generator, and moving the correct amount of distance according to the outer ring or the inner ring. It's going to allow you to figure out what is the input impedance, which then must be denormalized. You have to multiply that by Z sub C. And then the single stub tuner was sort of the pinnacle of our work here. We first plotted the normalized load impedance, converted it to an admittance, rotated clockwise away from the load until you, that should say intersect, until you intersect with the R equals 1 circle, convert the angle rotated to D1, then start with a short-circuited stub, rotate it clockwise until you reach an imaginary impedance equal and opposite the imaginary component of the point on the R equals 1 circle, convert that distance to D2.